Today we're going to look at my favorite representation of SP2R, the group of linear symplectomorphisms for the case of one dynamical degree of freedom, otherwise known as SL2R. It's my favorite because it is the simplest, the most practical, and the one that you end up working with the most. It's a representation in terms of polynomials. You might recall that we have been studying the Lie algebra of functions over phase space, that is real functions that map the space of coordinates and their momenta to the real numbers. The Lie bracket associated to this vector space of functions is of course the Poisson bracket. We've been pretty cagey about which set of functions that we want to talk about when we talk about the Lie algebra of functions over phase space. So for today's purposes, we're going to restrict to a very clear and simple class of said functions: polynomials. And since we're looking at a two-dimensional phase space, these are the polynomials in the coordinate q and momentum p. The Lie bracket, of course, of any two polynomials can be restricted by linearity to a Lie bracket amongst monomials. And given that the Lie bracket is made out of derivatives, partial derivatives, hopefully it's clear that the Poisson bracket of any two monomials is at worst a polynomial. Actually, for the case of n equals 1, it's easy to show that it's a very specific monomial. That is to say, consider the Poisson bracket of two terms, one q to the a, p to the b, with another q to the c, p to the d. We can compute this thing, and we get the very curious and interesting result that this is equal to the quantity AD minus BC times q to the a plus c minus 1, p to the b plus d minus 1. In other words, it's proportional to a specific monomial term. Putting aside for the moment that very interesting possible connection to the special linear group in terms of the integers, SL2z, let us instead make the observation that we have a polynomial whose order is a plus b, unnecessary, with a polynomial, dude, will look an equal. Anyway, a polynomial of order a plus b with a polynomial of order c plus d gives us a polynomial or monomial of order a plus b plus c plus d minus 2. And so it's helpful to remember the case that when you multiply two polynomials together, you're going to add the exponents, and when you take derivatives, that is to say the Poisson bracket of some polynomials, you're going to subtract from those exponents. Remember, monomials of different powers are linearly independent, so we can think of them sort of as basis elements. And so we can think of this as defining the structure constants for the Lie bracket for this Lie algebra of polynomials over phase space. So here's our first proposition of the day. The linear span of all the quadratic polynomials in R of QP forms an invariant subspace. Proof. We can look at our basic Poisson brackets and see, for the case of a plus b is equal to 2 and c plus d is equal to 2, that a plus b plus c plus d minus 2 is 2 plus 2 minus 2 is 2. You can do the arithmetic just as well as I can. But the point is that the Lie bracket closes on quadratic polynomials. And so we're done. So let's call this invariant subspace p sub 2 of q and p. It's spanned by the elements q squared, p squared, and qp. And so here's the main proposition for today. P2 of qp is isomorphic as a Lie algebra to SP2R, otherwise known as SL2R. Proof. Well, you might recall that the matrix Lie algebra for SP2R or SL2R is spanned by three matrices, sigma, sigma plus, and sigma minus. Sigma is just the diagonal 1 minus 1. Sigma plus is the upper triangular matrix, and sigma minus is the lower triangular matrix. Their Lie brackets are given like so. As we've just observed, P2 of Q and P is three-dimensional. It has three linearly independent elements, Q squared, P squared, and QP. So we're going to establish this correspondence, establish that they are isomorphic Lie algebras by brute force. That is to say, we're going to compute the Poisson brackets and show that they're identical to the Lie brackets of the matrix Lie algebra. To that end, define sigma now as minus QP, sigma plus as minus Q squared over 2, and sigma minus as P squared over 2. Now let's compute some Poisson brackets. The first of these, sigma plus with sigma minus, is easy enough. We pull out those factors of 1/2. We worry about our minus signs, we take our derivatives as appropriate, and lo and behold, we find sigma, that is minus QP. For the Poisson bracket of sigma with sigma plus, we can similarly compute, and it is once again pretty straightforward. There's really only one non-vanishing term, which gives us back 2 sigma plus. Similarly, we can do the same thing with sigma minus. Once again, we have only one real non-vanishing term, and lo and behold, we get back minus sigma minus times 2. And so we're done. Now there's a lot of very interesting representation theoretic content that we could do in terms of figuring out what the Casimir elements are, looking for unitary representations if they exist, and then coming out to figure out how we can find representations within the space of polynomials on which these things can act. All of this is interesting. I haven't introduced a lot of that technology yet, and I may, but if you're interested, write a comment or something, let me know, or shoot me a message, whatever. We can get into it if you want. But I think it might be at least useful to consider some simple examples that match up to stuff that we've done before, just to make sure we're all on the same page. We've seen before that sigma minus minus sigma plus generates rotations in phase space, right? It rotates Q's into P's and P's into Q's and so on. So let's see that in fact happens here by once again using the adjoint operator. You remember the adjoint operator from our second video in the series, right? The takes the bracket with this function operator. We can use it to exponentiate up these generators into the full Lie group. So in this case, our sigma minus minus sigma plus is going to be given by P squared over 2 plus Q squared over 2, which should look a lot like the energy function for our harmonic oscillator. But not quite. We are going to dedicate an entire video to that very interesting correspondence because it is very insightful. But for now, let's exponentiate that operator, add a little parameter, and see how it acts on functions on phase space. Once again, we can just simply act on the coordinate Q. So let's take various nested adjoints of this operator with Q. So we have the first one, second one, third one, fourth one. And we see once again, this pattern repeats. As is familiar by now, we can resum the entire series, this entire exponential, and find our cosines and our sines, and lo and behold, yes, we have rotations, once again, this time generated by polynomials and the Poisson bracket. I will leave as an exercise for you the hyperbolic rotations, which are just given by sigma plus plus sigma minus, that is minus Q squared over 2 plus P squared over 2, and also you can consider the dilatations, which are just given by sigma. And so this was a pretty easy one. This was n equals 1 is a simple case, hopefully connecting to something that you are familiar with. This was also a warm-up to do the general case, which is going to be very interesting and give us a very explicit representation of the full Lie algebra for SP2NR, which we will consider next time. So if you're interested, please stay tuned for that. Until then.